In this video, we will learn about significant figures and importance of significant figures in measurement. So let's proceed. Significant figures. Let's say we want to measure some physical quantity. For example, as you can see on the screen, a student measures the length of a line as say 6.8 centimeters. Now here we need to understand that the digit 6 is a certain digit. It is not 7.8 or 5.8. So this is certain. Now about point 0.8, we can understand this as the measurement may be slightly less than point 0.8 or maybe greater than point. What do we mean by this? For example, if we see the ruler which is measured or which has units in centimeters and millimeters. So let us say this is 1 centimeter, this is 2, this is 3, this is 4, this is 5, this is 6, and this is 7. Now we know that each centimeter has further subdivisions. That is, there are 10 subdivisions between each centimeter, and we know that length as millimeter. But when a system of measurement is used, for example, this ruler, and we say some length is 6.8, we are not exactly sure whether it is exactly 6.8 or lying between 6.7 and 6.9. And that's why we call this point 0.8 in this case as uncertain digit. Okay. So these digits in measurement, which are known with certainty, plus the first uncertain digit, they together are called significant. For example, if I say I have instead of a ruler, a vernier caliper, which can be used, in getting more precise measurements. Okay, so let us say the length of the line is now 6.84 centimeters if I measure using vernier caliper. Okay, now here, as previously discussed, 6 is a certain digit. Even 0.8 is a certain digit, but this last digit is uncertain because it can vary between 6.8 to 6.85. So again, the number of certain digits plus the first uncertain digit together comprise uh, significant figures. So in this case, there are three significant figures. And while discussing this concept, we understood or talked about precision. Now, what is precision? And how is it different from accuracy? Let us say I have a ruler which measures length as 6.8 centimeters. I have another unit, another measuring scale which is vernier caliper, which is saying it is 6.84 centimeters. Let us say I have an instrument which can measure up to three decimal digits. So I am able to measure the same length as 6.842 centimeters. Now what is happening here is 6 is a certain digit in this case, but 8 is uncertain. It can be 6.6 all the way up to maybe 6.9. Let us say 6.7 all the way up to 6.9. Here what's happening is it is 6.8 is certain, so 6.83 all the way up to 6.85. Here it is 6.841 all the way up to 6.843, let us say. So now what am I doing is I am making it more and more intricate. That means I am arriving at a higher level of precision. Here 6.8, here 6.84 is a certain digit. So precision is nothing but uh, more and more granular way of measuring. Whereas accuracy, let us say the because of the some of the instrument fault or incorrect way of measuring, I am arriving at these figures, and the actual length is, let us say, 8 centimeters. I'm just taking an example. The same line is actually 8 centimeters long, but because of faulty instruments or incorrect way of measuring, I'm getting these figures. So though my precision is increasing, my accuracy is not good, right? On the other hand, if I would have measured the same as 7.9 centimeters, 7.92 centimeters, and 7.921 centimeters, I'm increasing the precision and I'm also near to accuracy because 7.9 is very, very close to 8 compared to 6.2. So we need to understand accuracy is with respect to actual what is the value of measurement with respect to that what is the measurement value I'm getting, how much gap is there. Precision is how much detailed measurement I'm able to do because of the sophistication of the instrument. So we can have more precision, but still accuracy may suffer. We can have both precision and accuracy. We can, at the other end, have lack of accuracy and lack of precision also, right? Okay. Now coming again to significant figures. Why do we need significant figures? We'll understand that, and then we will calculate how to find number of significant figures of a quantity. Okay. So what is the importance of significant figures in measurement? So as you can see, the accuracy of the measurement determines the number of significant figures in the quantity. Okay. Suppose let us say instead of length, we see the diameter of a coin is 2 centimeters. Now, if a student measures it with a meter scale, which can read up to zero point 0.1 centimeter, as I said, that is 1 millimeter, this length can be understood as 2 centimeters, 2.0. That means it can be either 1.9 or 2.1. Okay. However, if the diameter is measured by a sophisticated instrument, which can read up to zero point zero 0.01 centimeters, so like a vernier caliper, so the diameter will be now 2.00 centimeter because here now the 2.0 is certain and it is either 1.9, I mean 2.0 or 2.02. So that last figure is uncertain. Okay. So and so on. So any measurement, it should be recorded keeping in view the accuracy of the measuring instrument. Okay. And that is why significant figures and calculation of number of significant figures of a quantity, you know, is important, right? If there are lesser number of significant figures, more will be the percentage error. If there are more number of significant figures, less will be the percentage. Okay. So now having understood this, let's see how to find the number of significant figures in a quantity. So the first rule is all non-zero digits are significant. As we said, if I talk about 6.8 centimeters, there is no zero here. All are non-zero. So that is why we say it is two significant figures because one digit is certain, that is 6, and one digit is uncertain, that is 8 after the decimal. Okay, 0.8. Now, if I say instead of this 6.856 centimeters, I have now four significant figures because there is no zero there. That is the first rule. All non-zero digits are significant. For example, 315.58 has five significant figures. In this, four are certain digits, 315.5, and 0.08 is the last eight digit. Is the last one is the uncertain digit. So all the certain digits plus one uncertain digit is the total number of significant digits. Now rule number two says all zeros between two non-zero digits are considered significant, as you can see here. So let us say instead of 6.8, I find it as 6.08 centimeters. I have now three significant figures because this zero is appearing between two non-zero digits. On the other hand, if I also have like 60.8 centimeters, still I have three significant figures because this zero is also lying between two non-zero digits. Whereas if I have 6.8 centimeters, then this zero is to the left of the non-zero digit. There is no other non-zero digit to the left of the zero. So I have to ignore this zero and only consider these two as significant figures. Hope this difference is understood, right? That is the second rule. All zeros between two non-zero digits are significant. For example, in this case, 5300,405.003. These two zeros are between two non-zero digits, which is 3 and 4. This zero is between two non-zero digits, 4 and 5. These two zeros are between non-zero digits 5 and 4, and therefore all of them are part of the significant figures. So total significant figures here are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 significant figures. This is rule number 2. Now rule number 3 says all zeros which are to the right of a decimal. Earlier we were discussing non-zero digits and zero between them. Now 0 to the right of a decimal point and also to the right of a non-zero digit. They are significant. For example, instead of 6.8, I write as 6.80 centimeter. So now this 0 is to the right of the non-zero digit, therefore it is considered part of significant figures and therefore I have three significant figures. Okay. Now there is one special case here. 0.04. If somebody writes it as 0.04050, it is also nothing but 0.04050. Now, if you see these things, first 0 to the right of the decimal, that is this 0. Okay, first 0 to the right of the decimal is not significant because there is no non-zero digit to the left. Okay, whereas this 0 which is to the right of the rightmost, okay, it is significant because the rule 3 says all zeros to the right of a decimal point and also to the right of a non-zero digit are considered significant. So here, how many significant digits are there? Only 4, starting from 4050. This 0 is of course between two non-zero digits, so definitely it is significant. So here it is 4 significant digits. Let's again understand it. 0.04050. This 0 is significant. This 0 is significant. So these are 4 significant digits. These two zeros are not significant. So therefore 4 significant digits. Okay. And that's what rule number 4 clarifies it further. All zeros to the right of a decimal point and to the left of a non-zero digit. In this case, I'll again write this. This 0 is to the right of the decimal point but to the left of the non-zero digit. And what does rule number 4 says? They are not significant. That is why we did not count the 0 in significant. Okay. Another example is 0.00043. All these three zeros are to the right of decimal point but to the left of non-zero digit, so they are not significant. So there is only two significant figures here. Okay. Now, also to be noted that 0 conventionally placed to the left of a decimal point is not significant. So in this is the decimal point and this 0 is to the left of the decimal point, therefore it is also not significant, which we understood just previously. Now, rule number 5 says all 0 to the right of last non-zero digit are significant. So in our case of 0.04050, this 0 is fulfilling this condition, right? The last of non-zero digit. Alternately, if I simply write 4050 also, this 0 is lying to the right of the last non-zero digit. In either cases, these are significant. So both these contain 4 significant figures. Okay. Now rule number 6 says number of significance does not vary with the change in unit. Very important. For example, if the length of an object is, let us say, 6.8 centimeters, or the same can be written as 68 millimeters, or the same can be written as 0.068 meters, or the same can be written as 0.068 divided by 1000. So 0.068. Okay, let's again see. This is nothing but 6.8 into 10 raised to minus 2. Okay, this is nothing but 6.8 into 10 raised to minus 4. Okay, we'll have one more zero here, so it will be minus 5. 6.8, if I put decimal here, 1, 2, 3, 4, 5. Yeah, 6.8 into this is kilometer. So in all these cases, we have two significant digits, two significant digits. These two are non-significant, so again two significant digits. These are all non-significant, so again two significant digits. So rule number 6 says number of significant figures does not vary with the change in length. Another example is shown here. The length of an object is 348.6 centimeter. It has four significant figures. So if the length is expressed in meters, it will be 3.486 meters. It still has four significant figures. Okay. Now the last rule is in a whole number, all zeros to the right of the last non-zero number are not significant. For example, 5,000 has only one significant. We need to understand this differently uh, from this. If you see 4050, this is a measurement. This is a measurement. That is 4050 meters. Whereas in a whole number means this is a number. Let us say 5000 pence. So in this case, it has only one significant. So if this value is part of a measurement such as length, which is a continuous number, then that 0 to the right of 5 here is considered part of significant figures. Whereas if I say 5000 pens, 5000 books and all that, which is a countable number, not a measurement, but a countable number, then the zeros to the right of the non-zero digit, extreme right, they are all non-significant. So if I say 5000 meters length, this is four significant digits because it's a measurement as we said, all the zeros to the right of 5 are significant. Whereas if I say 5000 pencils, this is a countable number. Therefore, these three are not significant and only one significant digit, which is 5. So, this difference we need to understand. So, if it's a measurement, 5000 meters, 5000 kg, say 5000 liters, then definitely all the zeros to the right of 5 are significant. Whereas if it is 5000 pencils, 5000 people, 5000 boxes, then they are countable. And then in that 5000, it's not a measurement of some continuous quantity, it is a discrete quantity. We call it countable, 1, 2, 3, like that. Then the zeros which are to the rightmost of a non-zero digit are not considered significant, and therefore we need to calculate significant figures accordingly. In this case, it is one significant figure, whereas in this case, these are four significant. Okay, last rule is clear. And we already understood importance of significant measure figures in measurement. We will see an example here, you know, when we express the result of calculation. Let us say I have 6.8 centimeters length of a line and another line is say, let us say 8.4 centimeters. Okay. Each of these values is having two significant digits. So their addition should also contain two significant digits. Let us add them 8 plus 4, 12, 6 plus 8, 14 plus 1, 15. So now it has three significant digits. So I'm not going to express it like this. I should rather round it off to 15 centimeters. This should be the answer. Because original numbers have two significant digits, the final answer should also have two, not more, not less. So if the answer is saying 15.2, which has three significant digits, I need to round off it to two significant digits because that's how the individual numbers are. Similarly, it is shown 3.2 centimeters is suppose the length and you want to find the volume, then you multiply 3.2 into 3.2 into 3.2. But when the answer you get and it contains more number of significant digits, you round it off so that final answer is containing same number of significant digits as each of the original numbers. So in this case, each of the original numbers has two significant digits. Therefore, final answer, that is multiplication of all these three, should also have two significant digits, and that's why it is rounded off from the value 32.768, which is the accurate value, to 33. It's a more precise value. I'll not say accurate, more precise. Okay. Okay. So that's the explanation here. Because there are only two significant figures in the length of the side of the cube, therefore volume should also have two significant figures only, not five. Okay. And one more thing we need to note. Let us say if I am adding two digits, that I will do here only. Instead of 6.8 plus 8.4, both of which have two significant digits, let us add 6.8 with 0.452. Now 0.452 has three significant digits. 6.8 has two significant digits. When we add them, it will be 7.252 answer. And the final answer, it should not have more number of significant digits. So now in this case, the input values are 6.8, which has two significant digits, 0.452, which has three significant digits. Then what do we need to do in the final answer? So if you see the sum of these numbers in this case should have the same number of significant digits as the shorter of as the one which has less number. Let us say here 6.8 is the lesser of the two in terms of significant digits. So the final answer should also have only two significant digits. So we need to round off 7.252 to 7.2 centimeters. That's what is explained here also. If we add three quantities, one is 2.7 meters, which has two significant digits. One has 3.68 meters, which has three significant digits. One is 0.486 meters, which is also having three significant digits. The final answer after addition should be rounded off such that it should have the minimum number of significant digits, that is 2. Okay. So the answer we get is 6.848, but this much precision is not correct. We need to round it off so that there are two significant digits, that is 6. Okay. Similarly, for multiplication and division also, we need to follow similar logic, right? Let us say you are multiplying these two figures, 3.003 with 2.26. Whatever answer you get, 6.78678 in this case, we know that this number, first number has four significant digits, second number has three significant digits. So this is the lesser of the two. So the final product should have only three significant. So we are rounding off this final product so that it has only three significant digits, and therefore we write it as 6.79. The same goes for D. Okay. And now when constants are used in calculation, what do we need to do? As you can see here, radius of a circle is mentioned as 3.35 centimeters. We need it to calculate its area, and we know that area is pi r square, where pi is a constant. So now here, if I multiply pi r square, okay, that is pi multiplied by 3.35. Okay, the final answer should have three significant digits. In order for that to happen, I need to take pi value accordingly. I don't need more precision here. So I take pi value as 3.14 multiplied by r square, which r is 3.35 in this case. Final product, you round it off such that it should have only three significant digits, because that's what this is showing. Now pi is a non-terminating decimal, so its value can go on increase. So the input with or number with minimum significant digits is 3.35, and the final product has to be rounded off to three significant digits. And that's why final product, though it is obtained as 35.23865 in this case, we round it off to 35. So basic logic is that when you are adding or subtracting or multiplying or dividing numbers, see that which of the numbers has the least significant digits, number of significant digits. The final answer should also be rounded such that it contains the same number of significant. So let us just conclude that here. I have case number one, 3.6 centimeters plus 4.85 centimeters. I will add them up. Let us say it is 8.45 centimeters and rounded off to 8.4 centimeters, because I want only two significant digits, which is the below. If I am in the same way 3.6, I am subtracting, let us say, from this 0.432, which has three significant digits. I know final answer should have only two significant. So let's say I'm getting this answer as 3.168. I round it off to a number with minimum number of significant digits. So that is 3.6 on the two significant digits. Here, after rounding up, it will be 3 point. Similarly, if I perform a multiplication, let us say 3.6 multiplied by 2.13. So I can perform the multiplication normally. In this case, the answer would be 36 3s are 36 to the 72, 108, 36 on the 36, so 46, 36 to the 72, so it is 76. And after putting the decimal, it will be 7.668. However, because 3.6 is having only two significant digits, final product needs to be rounded off to two significant digits, which is in this case 7.7. Okay. Similarly, if we perform division, let us say if I am performing division of 3.6 with, uh, let us say, very simplistic, we will divide it by zero point 0.5. So zero point 0.5 is having only one significant digit. And by the way, 3.6 divided by zero point 0.5, nothing but 3.6 into 2, which is 7.2, correct? Okay. It has two significant digits. We want only one significant digit, so it will be 7. This is how we perform calculations and round it off so that the final answer should have the same number of significant digits as the initial number out of the given inputs, right? That's what is explained here. So two examples. Second example says if a measured quantity is multiplied by constant, then all the digits in the product are significant because we are multiplying measured quantity by constant. Okay. For example, if mass of a ball is say 32.59 grams and mass of 10 similar balls we want to find, it is 325.90 grams, right? However, this zero is also significant. This is what we need to know. So this is what we earlier also noted. If it's a measured figure, then our zero at the to the rightmost is considered significant. And if it's just a countable, it is not countable. Hope it is clear. In the next session, we will understand about derived units and dimensional formula. Thank you.